All right, so let ABC be an acute triangle with circumcircle gamma. The angle bisectors of B and C intersected again at M and N. Obviously, we have an in-center, so I'm cheating here. Because I'm lazy. Oh, it already defines I. M prime and N prime. Let me delete the mess I just made. Wait, how do I? Yeah, there we go. Delete all that. Reflect. So you get M prime and N prime there. And show that the center of that circle lies on the altitude. Okay, that's kind of interesting. So the center of this circle, we want to show center of D lies on the altitude of A. Yeah, it's a very weird thing to show. I agree. Let me erase some stuff. Hide. Don't hide that. There we go. Obviously, we have two rhombuses here. So a rhombus, another rhombus. Might as well draw in the rest of the rhombuses. All right. Got a little rhombus there. I'm so happy it's not the orthocenter. Yeah, we did a lot of orthocenter problems. All right. Very random, I feel like. N prime intersect M prime is the circumcenter of ABC. That's a good point. I should draw that in. So we can call that O. This looks a lot like a problem I did recently on my channel where I had like two, like that problem was parallelograms and this one's like rhombuses. So yeah, O is the circumcenter. Oh yeah. I didn't do this exact problem though before. It was the last one I did do that exact problem, I'm pretty sure. All right. These problems are so tricky when you like show the center of a circle lies on another line. I feel like there's got to be some trick that is worth knowing for those kind of problems that I just don't know. Let's try a couple things. No, that doesn't do anything. Okay, so what would be the best theorem? Just see who's on. Hey, Ida Kumar, thanks for joining us. And also Dubai you. You probably joined a while back, but yeah, we just had a lot of people. So what is the best theorem to show that AD is perpendicular to BC? Could we show that? I guess one way we could show AB squared minus AC squared is the power of B with respect to that circle minus the power of C. That would be one way to do it. And AB squared we can kind of get using Pythagorean theorem a bunch of times. So yeah, how would we get the power of B with respect to this circle? I think that's like a reasonable approach. So yeah, what's the difference between the power of C with respect to that circle, or the power of B and the power of C? Maybe I could use Casey's theorem. Are there any circles that this circle intersects? Let me try some stuff. Oh, it looks like A, M, and M prime is cyclic. And it would be the same on the other side too, I guess. Yeah, once we know that, I think, oh no, it's not true. It's just an illusion. But let's see. Is that tangent? No. If we intersect AI with BC at P, that might help. So let AI intersect BC at P. Okay. Then A N prime PC is cyclic. Oh, do you mean arc BC or side BC? Oops. That's all right. But yeah, I really want to use my difference of powers idea. I feel like that has potential. So yeah, how do we take the difference between the power of B with respect to this circle and the power of C? And then show that's AB squared minus AC squared. I wish I just had one more circle that I could use. Let's think about this. So I'm gonna let me label this point right here. So that's point E. We know I like, let's see. Is this cyclic? I think this might be cyclic. No. Okay, I'll admit I'm kind of just guessing here, but yeah. But I have somewhat of an idea. Is I the midpoint of arc N prime E? I don't think so. No. There's something I'm trying to do here. I want a circle that passes through N prime and E, but I don't know if I'm going to be able to get it. Hey, Sai, thanks for joining. Yeah, I don't think I'm going to be able to get a circle that passes through N prime and E. It almost looks like CI is tangent to that circle, but it can't be true because, yeah, whoops. Did you say what isn't what true due to symmetry? That CI is tangent? CI is not tangent. Yeah, maybe I should draw the circle because we know N is the center of that circle and M is the center of this circle. So basically, I mean, we could reflect those circles, right? So maybe try drawing the perpendicular bisectors of N prime, I, M prime. Yeah, let's see. Hold on just a sec. Well, actually, if we draw the X centers, then A, N prime, B, and the X center, are those cyclic? Let me try that. Hold on just a second. So if I let CI intersect this circle at a point F, so F is the X center, is the CX center, and I think F prime, whoops. Is F prime the center of the circumcenter of AN prime? No, I don't know why I was thinking that. Okay. Never mind. Okay, so let me look at my perpendicular bisectors. Not sure if that. Oh, maybe it passes through another. It looks like it passes through that intersection point, kind of, right? So I think. Well, no, because on this side it doesn't. So I think that's just an illusion. Yeah. One sec, guys. I'll be right back. All right, thanks for waiting. This looks hard. because that circle is just so random. Yeah, what if I reflected the circle? I wonder if there's some kind of transformation I can do. Like, this is really random, but I'm going to try it. Yeah. Can I draw the circumcircle of A? Sorry, Timo, I missed your A M prime I. Let's see. And its midpoint. Do you mean a center? You could also try A N prime I. Oh, sorry. So I think those 4 points are linear. Yeah, they are. But what I was thinking, let me try something. What if I reflect I about AB and I reflect M about AB? So if I reflect M about AB, I wonder if, okay, yeah, it doesn't lie on that circle, but I feel like it's still a useful idea. So basically, the power of B with respect to this circle, it's the same as the power of B with respect to that circle. Wait, what? It didn't work. Oh, I need I need this circle. Let's see. So yeah, I reflect and then reflect again. Can we say anything about this point right here? It's like a double reflection. M. Maybe I really can't say anything about that. So G and F, they're the centers of the circles AN prime I and AM prime I. Let me draw. So this is a midpoint right here. So H and J are midpoints. So oh, wait a second. Maybe I want to let me delete this and this. Maybe I want to reflect it about point J. So basically form a bunch of parallelograms. If I reflect I about point J, and I reflect M about point J. So MM prime, so MM prime BC, I think is a parallelogram. If you reflect twice like this. And I is the reflection Yeah, so we have like two parallelograms, AI, B, I prime, and A and MM prime B. So yeah, so then if we draw the circumcircle of M, oh, but then I don't think B with the same power. Yeah. But that would be the power of A with respect to that circle. So basically, we want to show the power of A with respect to this circle. Okay, so this is kind of weird, but I think this circle intersects. I think I have a weird solution because I think these 3 points are concurrent. Yeah. So the power of A with respect to this circle right here, that's AK times AI prime. All right. See you later, PC. Thanks for joining us. So yeah, this. Let's see. Okay, so I'm going to construct the same circle on the other side. So M prime CB is a parallelogram, and I'm going to do the same thing with point N prime. So we have this circle right here. ANB, yeah, ANBN prime is a rhombus. Yes, that is correct. Maybe, you know what? Maybe we could use the gliding principle, because if we have, but they're not similar rhombuses. That's the thing. Basically, these circles are congruent. If we can show the difference between the powers of them with respect to A is AB squared minus AC squared, that would solve it. What was I thinking before? So, oh yeah, so so yeah, if I draw this intersection point, let me delete the circles of AIM prime and AIN prime just for now. So, yeah, so it looks like this. It looks like these are collinear, right? So if I can show that, I want to show AK times AI prime. That's the power of A with respect to this circle. And the other is AI1 prime times AF. I want to show the difference between those is AB squared minus AC squared. But AI prime is BI and A. So yeah, what is AK? How would I get that? Maybe it's worth drawing this point right here. So angle AKM, because AI prime is parallel to BI. So angle AKM is equal to angle IBC. So I could try the same with let's see. So yeah, angle AKM is equal to angle MBC. So I think if I draw this point, I think, see you, Enrique. Thanks for joining. I think AKL is similar to IBC. So AK over IB is AL over IC. I wonder if this is like enough to solve it actually. Let's see. Let me write this out. So let's see. And if we draw, I think N, N prime, and F are collinear. So we would also have okay, and yeah, I think it's also collinear with this point right here. So is it? Not sure about that. Let me check. No, I think the figure is just like this. Yeah. So this one looks tricky. I think it might take a little bit of work. Solve. All right, Serdar, feel free to share. Let NC. So I should probably erase everything I've done so far. So let's see. But I'll just read through it first. Cut the circle at, so NC cuts the circle AIB at J. I'm guessing that it's that circle. Okay. Let me delete a whole bunch of stuff I've added. Let me delete this. Let NC cut, I'm guessing you mean this circle at J. So those are the incenters and excenters, right? So this is J. K. Oops. Sorry, making room here. Let me rename this. So we have J n prime m prime k is an isosceles trapezoid. Wait, what is J? Oh, I doesn't even have to be the incenter? That's crazy. Well, if that's true, well, so then would these be like parallelogram, or I'm trying to think how that would work. So would n prime, would this be a parallelogram or a kite for the result? Like if I were arbitrary. Not sure. Okay, so for now I'll stick with the incenter, but that's really interesting that I doesn't have to be the incenter. So what is yeah, what is K? You said J n prime m prime K is an isosceles trapezoid. Oh, let NC, no wait, we have JK. So what is this, the J and K you were talking about? Oh, maybe you meant this point. So wait. Let NC.
Where's K?
K is right here.
Oh, God.
But Serdar, what were J and K? Is this the right J and K?
And C cut the circle at J. And C.
This circle? So
No, not this circle, our main circle. I n prime m prime circle.
oh, that circle. Ah, my bad. Okay.
I didn't use these circles.
All right. So I will delete those points. Sorry. Oops. Sorry. Sorry about that. Let me move it back here. Okay. So we draw that circle and just trying to make it look nice. So that's J. And K is where MB cuts it. So this is K. Then J n prime m prime K is an isosceles trapezoid. Let's think about that. If we can prove that, that solves the problem.
There are two nice observations too. I wrote.
Okay, so AJ m prime C is cyclic.
Yeah, but I couldn't prove.
All right, let's see if we can prove it. And AN prime KB is cyclic. So if we reflected all four of those points, really we want to show the reflection of K over AB lies on the circle. So So what if we like reflected, okay, we want to show the reflection of K over AB lies on the circle. So that's kind of the same. We could try, yeah, if you reflect both I and M, we could use like a similar idea. The cyclicity is equivalent to proving Km prime is parallel to BC. Might be. I think so. So yeah, I still like the idea of reflecting M prime over this midpoint right here. Let's give it another name instead of J1, I don't know, P. But basically, if we reflect M prime over P, it forms a parallelogram. That's what I like about it. So this prime forms a parallelogram with MBC. And if you reflect N prime over point P, you just get N. So we have to reflect I over P. So it's kind of like saying, yeah, we would have like a cyclic. And then A, K, and I prime would be collinear. And yeah, so maybe it's like, yeah, so we let this be the point that makes a parallelogram. We let it intersect the circle at K prime. And then we try to show that this K prime N and that are cyclic. So that's the same as showing angle AK prime M is 180 minus N prime IM. Yeah, it's like we want to show, if we can show AI prime is parallel to BI. Okay, so here's kind of my strategy. So we let this be the point that forms a parallelogram, M double prime. We let that intersect the circumcircle of ABC at K prime. So yeah. I think you're right. Yeah, how do we show A is the circumcenter of that? Is it an angle chase? Okay, I have some ideas. We want to show angle n prime m prime I is this angle, angle NAB. I'm still thinking about it this way. Let's see. But I like that idea that you just mentioned. We want to show it. So let's draw that circle. Okay, so AJ, let's see, AJ is intercepted. So we know AJMC is, oh, I think we have to prove it. Yeah, if that's true, we're finished, yeah. So angle ACJ. Yeah. I wonder, are these circles the same size? Let me check something here. So if I take angle ABN prime, 21.2, ACJ, yes. Basically, we want to show the circumcircles of AN prime B and ACI are the same size. AN prime B and ACI. How do we show those are the same size? Well, the circumcircle of AN prime B is the same size as the circumcircle of ABC, which, yeah, okay, I think we've solved it. So the circumcircle of AN prime B, is the same size as the circumcircle of ABC, which is the same size as the circumcircle of AIC. Is that right? Oh, we want this circle as AM prime C, yeah. So that's it. So yeah, it's so yeah, I think that solves the problem pretty easily actually. So I'm gonna write it out. Let me see what I can delete here. Obviously, I don't need that. Don't need that for that. I don't even think I need this necessarily. Okay, so, oops. So what points did we add? Let's see I intersect. So yeah, my proof is going to overlap the figure a little bit, just because I think it's hard to make it not happen. But let's see I intersect intersect the circle n prime I again at j, and define k similarly. Okay, so define k similarly. And then the circle, so we have the circle A n prime B is congruent to the circle A n B, which is congruent well, I'll say that's the same as the circle AMC, which is congruent to AM prime C, that circle. And once we know that, oops, that looked weird. I have to add, oh, the $sign. So if those circles are congruent, and then also angle A, we want to show angle ABN prime is equal to angle ACJ, and that's an easy angle chase. So we have angle ACJ is equal to angle ACN, which is equal to angle ABN. Which, what was I doing? Which is equal to angle ABN prime. So that means that AN prime is equal to AJ, since the circles have the same size. That's pretty elegant, right? So thanks.
Sorry, why is it equal to AJ? AN dash equals to AJ.
Yeah, because the circles through A, N prime, and B is congruent to the circle through A, M prime, and C. So these two circles are the same size. So if you have equal angles, if angle AB prime if angle ABN prime is congruent to angle ACJ, and since you have the same angles and they're in circles of the same size, they have to intersect segments that are the same length. So
Yeah,
that
I was thinking about the same thing. So it's an ambiguous, right? So how are they having equal radiuses as circles?
yeah, so
I
they have
mean,
the same radius, right? And you have the same angle intersecting them. So yeah, they have to be the same length. So once we know that, we can then prove that nj. Yeah, someone help me out here with the ending and prove that I. So I define j to be on the circle. So I mean, oh, then we want to show aj m prime c is cyclic, or yeah, okay. So and then once we know those are cyclic, yeah, I forget how we finish it from there though. So maybe I'm just getting ahead of myself, but yeah, so
yeah. So an equals to an dash equals to aj, right? So
yeah,
that makes a is the center
A is
of
the sort of
triangle.
center of that. Yeah.
Yeah.
So J as CI intersects A M prime C. So if we define J this way, we should be able to show it lies on these two circles, I guess. Oh, did I skip a step? Because I just kind of assumed J lies on that circle. So I
Yeah,
kind of
actually, if we define J as Ci intersects A M prime C, then we can easily prove N prime C, M prime K is isosceles trapezoid. Then we have to prove I is on this circle.
okay. So you're right. I left out a step here. I'm sorry. So but okay. So I want to show AJ M prime C is cyclic. I didn't do that. I kind of just assumed it. Whoops. Yeah, I skipped a step here. Let me add it in.
We can define J differently. Actually, maybe it makes it easier.
Okay, so let me just think for a second if I can define it this way, if there's an easy, and otherwise I'll define it the way you mentioned. So hold on just a second. Let me think. Yeah, I think you're right. So you think it's better to define J as the intersection of the circle AM prime C, right? Or BJ and H collinear. That would be interesting. No, it's off by a little bit. But okay, so if we define J that way, like you mentioned, then we would have to show CJ and I are collinear basically. So and is that easy to show? We just have to show angle JCM prime is equal to angle ICM. Or we could show JCB as ICB. So JC, yeah, what was your idea, Serdar?
We will prove that I is on the isosceles trapezoid. I is on the circle of isosceles trapezoid N prime J, N prime K.
M prime J. Okay, so you define K similarly, right? So you basically, so you're defining K this way also, right?
Yes.
And okay, so these circles are the same size. And then from there, we know that AN prime is equal to AJ, right? Yeah, we didn't need, okay, so let the circumcircle AN prime C meet IMN at J. So like that, and then define K similarly, and then everything else still applies, right? Maybe the angle chase might not work though. Let's see. So we still have the congruent circles.
Yeah, I still doubt the two triangles are congruent or not, A and dash B and AM dash C. So if you look at the triangles, if they have to be congruent, then AB should be equal to AC. So that is not the case, I think.
Well, I guess so. The circle through A, N prime, and B, it's the same size as the circle through A, N, and B, right?
Right.
And the circle through A, N, and B is the same as the circle
Yeah,
through
yeah,
A.
that makes the radius same. But if you take AB and AC out of the congruency, you would find that the two sides of the triangle are equal, which may or may not be. AB and AC, why would they be equal?
Yeah, AB and AC are not necessarily equal, but the circles through A, N prime, and B, and the circles through A, N prime, and C are equal. So yeah, A, B, and C are not necessarily equal. So yeah, I'm not saying these I'm not saying these triangles are equal, just the circles around those 3 points are congruent.
Oh, sorry. I just uh, saw the notation differently.
Oh, it's all right. No problem. Um, so yeah, so then can we show that, so angle C, so is there another way to show these angles are equal? So angle ACJ, can we show CJ and N are collinear? So angle ACJ is a MJ. So ACJ is a M prime J. M prime C and B prime N intersect on this circle.
Maybe we can go on.
Okay, let me draw it the other way. Because if M prime C and B prime N, that's interesting. So yeah, how do we prove these different collinearities? Let's see. I want to see. I feel like it shouldn't be that bad to show that. Oh, whoops. J and I are like overlapped. There we go. I feel like it shouldn't be that hard to show that CJ and I are collinear, right? It feels like it has to be true somehow. So, I mean, it's the same as saying that angle JCA is half of angle C, which is the same as saying that J and prime A is half of angle C. Let me try some stuff here. E, B, C, and I are cyclic. Let's see. What is E? Oh, that the point where they concur. Interesting. So yeah, it can't be that hard to show that CJ and I are collinear. It feels like, or at least I don't. Maybe it's harder than I think, but how would we do that? Well, we could show C or CJ and N. We could try to show are collinear. So we could show BN prime I and CM prime I are similar. Huh. I think you're right. So we could show BI over CI is equal to, I think you're right there. BI over CI is BN over CM. Is that right? Let me just do a check on that just to be sure that it's actually true. BNI and CMI are oh, yeah, because I erased that other circle, which, let's see, let me, yeah, I erased this circle and I erased this circle. So, because IMC equals BAC, equals BNI. Okay, so if we know that BN prime I and CMI are similar, how would that help? I'm just thinking through it. BI over BN prime. So I agree with that. Would that solve the problem? Or do you think that would solve the problem? So I understand BI over BN prime is CI over CM prime, and that shows that those triangles are similar. What would be the next step after that? So do you guys want to move on to the next problem? I feel like we're on the right track here. It's just we spent a while on it.
Yeah, just 5 minutes. It's pretty good.
Or did you say wait another 5 minutes?
Oh yeah.
Okay. So Timo thinks he has a solution. So let's see. So Timo. So once I know Bn prime I is similar to Cm prime I, where would I go from there?
Is there a way to prove CM dash as an angle bisector too? Because CI is clearly an angle bisector.
Oh, hold on one sec. Okay, see, I agree. I is the center of a spiral similarity that takes those two triangles. I agree with that. What were you saying, Sai?
Yeah, we have to prove CM dash and I collinear, right? Sorry, CJ and I collinear. I'm sorry.
BK and I, yeah. If you can prove BK and I are collinear, I think that would get us closer.
So could we prove CJ as an angle bisector?
If we could show that BK is an angle bisector, then yes, that would help solve it. Maybe we could label this point here. I don't know, but let me read what Timo said. So yeah, I agree. IN prime N prime is similar to IBC. I agree with that. Thus MAC. So I guess that same spiral similarity would take B to the midpoint of arc BC, right? Because we know the circumcenter of IBC is the midpoint of arc BC. So maybe that's pretty close to, so thus angle MAC is equal to angle CAM, which is equal to angle CBM, which is equal to angle CBI, which is MN prime I. Okay, so MAC is MJC. MAC. So I think there's probably a typo somewhere there. So MAC. Oh, I think you mean, yeah, M prime JC. Okay. MAC. But how do we know that M prime AC is M prime JC? Right, M prime. Because M prime JAC is cyclic. I thought we wanted. Oh, okay. You're defining it that way, and then you want to show. So I guess we defined M prime JAC to be cyclic, right? So we have M prime.
Yeah.
Prime
Yeah.
I.
Then we are trying to prove CJI dash S,
Oh, that
CJI S.
shows that these are collinear. Okay, so basically
Yeah,
showing I, J, and C are collinear because M prime N prime I.
yeah, it's very confusing what we assumed.
Yeah, no. Okay. So okay, so there's a lot of steps here, but I like it. So I'm gonna finish writing this up. Okay, so it's very interesting. So we don't know this yet, so I'm gonna delete it. But okay, so we have BI over CI is equal to BN over CM. Wait a sec. So is BNI similar to CMI? Let me check that. So
Yes, BNI and ZMI are similar because angle IMC is equal to angle 2 times angle IAC, and that's 2 times angle BAI, and that's angle BNI.
okay.
And those two triangles have two equal sides, so they are similar.
All right, I like it. Very good solution. So I and B, so that means that IMC is similar to I and B. So yeah, I'm just assuming the in-center, x-center limit here. Maybe I'll write it out in the end. So we have Bn prime over Bi is equal to Bn over Bi, which is equal to Cm over Ci, which is equal to Cn prime over Ci. And then we could show that the angles between them are equal. So angle N prime Bi is angle ABI minus angle ABN prime, which is equal to angle ABI minus angle ABN, which is equal to angle B over 2 minus so that's half angle minus angle C over 2. So then similar, and then okay. So we have similarly angle JCM prime is equal to that. So angle M prime BK is equal to angle M prime CJ. So those triangles are similar. Oh, is it that? There we go. So triangle n prime bk is similar to triangle n prime cj. And that means oh, I'm sorry, I should be I, not.
Now I is the center of the spiral similarity that sends n prime m prime to BC.
Yes. So I is the center of a spiral similarity taking triangle I n prime m prime to IBC from that. So and then now we can do an angle chase that shows that so we have angle I m prime n. So yeah, we can just write it out now. So angle I m prime n prime is equal to angle ICB. So, and we want to show that's angle JCB. So, okay, I know you wrote this out in the chat. Let me just think about it. So we want to show I m prime is also JCB.
Now we have yeah, angle ICB is equal to angle NAB, and this is equal to angle N prime AB, and this is equal to angle N prime KI.
N prime AB is N prime KI. We only know that if
yeah, it's 180 minus N prime KB, and B, K, and I lie on one line, as we define K.
Oh, so we define K to be the intersection of BI with the circle? Is what you're saying?
We define K as the intersection of BI with the circumcircle of A n prime B, and in the same way J, and now we have the circumcircle of N prime, J, K, and M prime, and there we try to prove that I lies on the circles.
Oh, I was thinking of it a little differently. I was thinking that we define K to be the intersection of these two circles. It should still get us to the same place. Like, I was defining K as the intersection of these two circles, and then I want to show those are collinear. But I think
yeah, okay. It
should be the same. Yeah.
The same, yes.
Yeah. Let's see. I think your angle chase was actually that you wrote actually kind of did it that way. So we have MAC. Okay, so you showed that. Let's see. By what you wrote in the chat, MAC is so N prime AB is the same as N prime BA, which is the same as N prime KA. So
I did it on the other side, but now we can say angle I M prime N prime is equal to angle IK N prime.
Okay, so let me write it out. So angle I M prime N prime is equal to angle IK M prime.
Yeah, and angle N prime AB, which you wrote already down, is equal to angle N prime KB. 180 minus N prime KB.
Okay, so this is like that.
Yeah, and therefore B, K, and I are collinear.
Okay. So this is 180 minus n prime KB, and this is angle IK n prime. And so, okay, so the two of these imply that IK and B are collinear. All right. And then similarly, I, J, and C are collinear. So once we know that, then we know that A is, we can show that from there that A is the circumcenter of NN prime J. So I'm running out of room here a little bit, but
yeah, I would say now we know D lies on the angle bisector of n prime A J.
okay.
And
Yeah.
then, and with this fact, we can show that D lies on the altitude with an angle chase.
Okay, I'm literally just going to write that out now. Just, but thanks so much for your help, Timo. It was really helpful just talking it out like this. So D. So I'll just say angle angle ACJ is equal to angle ACI. So ultimately ACJ is going to be equal to A B prime N prime A B N prime. Yeah. So yeah, I'll say like this: angle ACJ is angle C over 2, which is angle ABK, and that means that AN prime is equal to AJ.
I think it's ABN prime, nicht ABK, not ABK.
Oh, sorry, ABN prime. Yeah. So yeah, it's really that would really be angle ABN, which is angle ABN prime, and that means that AB is perpendicular to N prime J. And
I would say we also have to prove the similar case that AK is equal to AM prime.
yeah,
and then we know that DA is perpendicular to N prime J.
Okay, so yeah, so maybe I'll just write up here, and then similarly, AD is perpendicular to KM prime. And from there, basically, that means that so that means that that's an isosceles trapezoid. So yeah, how does that show AD is perpendicular to BC? So we have an isosceles trapezoid, right?
Yeah, and I think now it should be in the angle chase, because since DA is perpendicular to N prime J, we know that DA is the angle bisector of N prime AJ.
Okay, so really we don't even need this. If we know if we know, I'll say this implies AD bisects N prime AJ. And then by an angle chase, that means AD bisects BAC, well, not BAC. But by an angle chase, I mean that means AD is perpendicular to BC. That shouldn't be that much harder. I'm just going to write that for now and then move on to the next problem. By an angle chase.
Yeah, it should be trivial though, by an angle chase. It's
Yeah.
enough, I would say.
All right, thanks for your help, Timo. So I will move on to the
Yeah,
next.
just to sum it up, I really would like to, would you go back to the previous question? Just a 2-minute overlook. Yeah,
So the whole thing is going to be on YouTube.
I got about IJCR collinear, and then Timo tried to prove like AJ is equals to AN dash, and after that I could not follow up.
Yeah, if AJ is equal to AN prime, then A
Yeah.
lies on the perpendicular bisector JN prime, and D
Yeah.
also lies on the perpendicular bisector JN prime because it's the center of the circle. So this is a kite, AN prime DJ. So AD bisects that angle. That makes sense. We can talk about it more later on
Got it. So, oh yeah, it's
yeah,
clear. Thanks.
just because we've only gotten through 3 of them. We only have a half hour left, so this one looked kind of fun. So let me, maybe we can get through this quickly. Let's see. So we have a parallelogram ABCD. P is on BD. The circle with center P passing through A intersects. Okay, so it cuts AD at Y and AB at X. And AP intersects BC at Q and CD at R. And we want to show angle XPY is XQY plus XRY. So it's kind of like an elegant statement. All right. That is an interesting statement. So yeah, is there a way we can break up XPY into each of those individual angles? Maybe angle XP, no, that wouldn't make sense. But yeah, actually, let me try this. I think maybe we have XPA is equal to XRY. No. But maybe XPA, so XPA is angle XRP plus angle RXP, right? So we want to show RXP plus RYP is XQY. And maybe is RXP equal to that? Yes. So, and that would mean those are similar triangles, which would mean, so that means Q and R are basically inverses of, so P is the center of the circle. We want to show Q and R are inverses. So we want to show PQ times PR is PX squared. And maybe that's similar triangles because
AP over PQ equals to BP over PD, and RP over AP equals to PD over PB. So they're equal. So PX squared equals to PQ multiplied by PR.
yeah, so I think that solves it. I think yay, we got it fast. Okay. We only got through 3 problems so far, but this one I think, so we have AP over PR is equal to BP over PB. And then we also have AQ over QR is BQ over QC. Oh, actually, you know what? It's probably better to say AB over RD. Yeah. Or actually, I don't know. So
It doesn't matter actually.
yeah, it probably doesn't matter. So AQ over QR is BQ over QC. And then, so we wanted to show that PQ times PR is AP squared. So if we multiply the two, is that what we get? BP.
Actually, we should write AP over PQ.
AP over PQ instead.
Yeah.
Um,
AP over PQ equals to PD over PB, and PR over PA equals to PD over PB, so they're equal.
PD over PB. And we could just say that that's
AP over PR.
AP over PR.
No,
We can
won't change
directly
that.
say that
It will stay same.
we can directly say that PD over PB is equal to PA over PR.
PD over PB is PA over PR.
PR over PA, I mean. And
AP
we
over PR.
can write it directly next to the first equation because we have PD over PB, yeah, or in this way.
Okay. So that means that PA squared is PR times PQ. Okay. And that means that triangle XPQ is PXQ is similar to PRX. And then that means that angle PQX is equal to angle PXR.
PXR.
And then similarly, angle PQY is equal to angle PYR. All right. And then from there, it's just, we can finish pretty easily. So angle XPY is equal to angle XPA plus angle YPA, which is equal to angle XRP plus angle RXP plus angle YRP plus angle or plus angle RYP. And that that's equal to angle, yeah, I'll just write the last line. So that's equal to angle XRY plus angle PQY plus angle PQX from what we had above. And that, whoops. Yeah, and that, yeah, I'm literally just going to copy this just because I'm so lazy. All right, and then move on to the next problem. All right, thanks everyone for your help on that. That was an easy one. All right, so now I will go on to this problem. Okay, so this one was this year. So we have a triangle ABC. Oh, this one looks a little tricky. Let's see if we can solve it in the last 20 minutes. So the end center is I. BI meets AC at D. P is on CI such that DI is equal to DP. Okay, this is P. E is the intersection of BC with the circumcircle of ABD. Okay. So, whoops. So this is E. Q is the intersection of EP with the circumcircle of AEC. And so we call that Q. I have to rename it. Is that the right? Yeah. We want to show PDQ is 90 degrees. Okay. Oops, don't want to hide point Q. All right. So yeah, DP is equal to DI. Maybe I could just hide this circle. We know that DP is equal to DI. Whoops. So DE, let me try something. Okay. Basically, let me try just for the heck of it, drawing the midpoint of this. So we want to show like this is a harmonic bundle. Well, not necessarily, really. I want to show PDQ is 90. Is there another point on a circle? Is PCQ 90? Yes. So we want to show PDQC is cyclic and PCQ is 90. How would we show that? So PCQ is it's ECQ minus ECI, and ECQ I wonder if P is the in-center of EDC. It kind of looks like it, doesn't it?
EQ equals to AQ, I guess.
EQ is equal to AQ. So yeah, P is like the in-center of EDC. I think that's an angle chase. And you said EQ is equal to AQ. Is that obvious? So if this, someone wrote something in chat, is ID equal to IE equal? So yeah, is it obvious that this is the in-center? And is DE parallel to AB? No, DE is not parallel to AB, but P is the in-center. Is that an angle chase? So
it should be an angle chase, I think, and then we get that IDA and ICQ are similar, I would say.
IEA and ICQ? Or
IDA.
IDA and ICQ. Okay. I'm sorry, IDA and ICQ. Okay, because they're both right triangles.
We need some more things, but at first we want to prove that P is the in-center of DEC.
Okay, I'm going to do that.
English, I would say.
All right, so first I'm going to do that. So obviously P lies on one of the angle bisectors by definition. We could try to show that, so since angle IDP, so since this is isosceles, then yeah, so it should follow, yeah, let me just,
so we can get angle CID and we can get angle BDC, and thus we have to get angle PDC, I think.
we'll write it like this. Angle EDP is angle BDP just thinking of the most efficient way to do this.
No, I don't think that we, or I think we want to get angle PDC.
PDC. So we want to show PDC is half of, okay, because since this is cyclic, EDC is angle B. So we want to show that PDC is half of angle B.
Yes.
So angle PDC is angle BDC minus angle BDP. Which is
Yeah, I think I got it. So angle PID is equals to C by 2 plus B, right? Angle C by 2 plus B. So since DI is equals to DP, so we'll get angle IDP, that is 180 minus 2 times of angle C by 2 plus B, and by that we could subtract that from angle BDC, that's equal to, I guess, B by 2 plus A.
okay. So
Did it make sense?
yeah. So I'm going to write out exactly what you just said. So BDC is A plus B over 2. And this simplifies to that almost makes it look like 0. So what do we want it to equal? We want it to equal angle B over 2. But that doesn't.
Yeah, like I said, the angle chase I did, I got P as the in center.
Yeah, so let me just think this through. So PDC, it's BDC minus BDP, okay? BDC, which is BDC minus IDP, okay? BDC, that's A plus B over 2, that's right. And IDP, that's 180 minus twice. Okay, we need 180 minus twice that. And then I think we should be good. Okay. Is that right? So it's 180 minus twice angle. Shouldn't this be angle C over 2 plus angle B? Yeah, okay, that's correct. And then from there, and that's angle EDC over 2. So that means that P is the in-center of triangle EDC. What the heck? That's not what I wanted. Let me do it like this. There we go. And once we know that, then how close are we? So that means angle PDC is B over 2, and angle EQC, can we show that's also B over 2? So EQC is AC. Let's see in the chat. Okay, I'm going to just copy what Hakan said. So thanks for typing it out. I should probably just do this, right? All right. Maybe put some backslashes in here just to break it up. Maybe that'll work. Ooh, that worked on the first time. That's amazing. So maybe a couple extra spaces here and there, but overall, not bad. I like it. So angle DCQ is ACQ, is AEQ, is AED plus DEP, and AED is B over 2, and DEP we're leaving as DEP. B over 2 is EDP. EDP plus DEP is DPQ. So DPCQ is cyclic. And that means that angle PDQ. But wait, how did we know that this was a 90-degree angle here? PCQ. It's probably obvious, right? But yeah, so PCQ is equal to, yeah, it's obvious. So that's angle C over 2 plus angle ACQ, angle C over 2 plus angle AEQ. Wait, is that obvious? So ACQ is AEQ, which is AEP. How did we do this? AEQ is AEP, which is okay. So AED plus angle DEP. DEP is DEC over 2. I'll just say that's angle DAB over angle A over 2. I'm gonna just cheat here. So PCQ is equal to 90. So that means angle PDQ is 180 minus angle PCQ is equal to 90. All right. So I will move on to the next one. Whoops. So we got through those really fast. So I think we've done, wow, we've done all of them except this one. And this one actually, I don't even know if it's that hard. But so just based on a quick feeling. Let's see. So we have A, B, N, C, D, M. So N and M are the midpoints of arcs. That's weird. So let me use my perpendicular bisector tool. N is the midpoint of BC. Wait, C, they mean CM and B? Oh, maybe it's the others. Okay, so M is the midpoint of like the bottom arc. Okay, so let me zoom out or maximize. So ABC. Oh, we want, yeah, AB, so this is N, and this is N. So, oh, but it says clockwise arcs. Maybe they mean arc BA. Yeah, this is the clockwise arc. Okay. So that's N and M. We could call the center of the circle O. So it lies on those two perpendicular bisectors. P is the intersection of AC and BD. All right. Q is on MB, such that PQ is perpendicular to MN. That's weird. Okay, so we draw the perpendicular. Let's see. Let me space these apart a little bit more. Yeah, that looks better. So we draw the perpendicular to MN. And we let it intersect MB at Q. And R is on MC such that QB is equal to RC. This is really weird. Okay, this is maybe a pretty hard problem. Where's the compass tool? Compass. Here's the compass. QB is equal to RC. That's weird. So that's point R. And we want to show the midpoint of QR lies on AC. That is so weird. Okay. I think it's worth drawing NO and MO just but let me space things out a little bit more. So PQ, yeah, we want to show that PQ is perpendicular to MN. So
We know PQ is perpendicular to MN.
yeah, we know. Oh yeah, I'm sorry. We know PQ is perpendicular to MN from the problem statement. We want to show the midpoint of QR lies on AC. So BQ is equal to RC. It looks like, let me draw the midpoint. Maybe we have some congruent triangles. I don't think BQF is congruent to CRF, right? That would be weird. But let me check. Yeah. Maybe it's like some projective geometry thing. Let's see. Kind of like that diagram. So if BQ is equal to CR, it feels like we need to have some congruent triangles to prove this then. So what congruent triangles can we find with BQ and CR? CRN.
I think it's beneficial that taking the circumcircle of MQR and intersect it with circumcircle.
Okay. Did you say MQR?
Yes, Michael point we can use because BQ equals to CR.
Ah, I think you're right. Yeah, I like that. So since BQ is equal to CR, is this like I think these are tangent. They look tangent, right? Oh, actually, I'm not 100% sure. Let me play around with it a little more. But it's
Cannot be.
No, they're not.
MQ must be equal to MR.
They're not tangent, but it's close. But basically, okay. So really, we want the other intersection point. It's G, yeah. So basically, yeah, since BQ is equal to CR, that means triangles GQB and GRC are congruent. So G should lie on the
intersection point is midpoint of arc BC.
Yeah, it's the antipode of N. So NO and G are collinear. Okay, so NO and G are collinear. We want to show the midpoint of QR lies on AC. Does the midpoint of QR lie on G? No, F doesn't lie on GN necessarily. But the midpoint of QR, yeah, maybe it's like, so maybe I should draw the center of that circle you just said. So the center of E. And basically, FH is perpendicular. maybe it's like a butterfly theorem. It feels kind of like a butterfly theorem. Because if F is the midpoint, NQF is congruent to NRF. All right, so NQF.
We have to prove that actually.
Yeah, we have to prove that. But we know NG is a diameter. Yeah, so we want to show NQ is equal to NR. Is N, but we know, I feel like we're pretty close, because I think QGR is isosceles. Yeah, so and GN is a diameter. Okay, I think we're really close to solving this. I'm going to stop. Is OQ equal to OR? No. So OQ isn't equal to OR, but yeah, I feel like we're pretty close on this one. I'm going to stop and leave it to the viewers to solve the rest of it, just because we're out of time. But yeah, this is pretty cool. So we spent a while on that one problem. Part of it was my fault. I was just pretty slow on it. But thanks everyone for your help. We had a pretty good turnout today. And thanks everyone on YouTube for watching. So like and subscribe, and I'll see you next time. Have a good one.